Dielectric materials used in the manufacture of capacitors are characterized by conductivities that are small but not zero. Therefore, a charged capacitor will slowly lose its charge by leaking across the dielectric. If a certain 0.2 times 10 to the negative 6 Farad capacitor leaks charge such that the potential difference decreases to half its initial value in 5 seconds, what is the equivalent resistance of the dielectric? Blah, 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 is what I'm hearing. It's like, we're going to just be using the same equation, but this time it's leaking its charge. So it's decreasing. And if it's decreasing, we immediately want to leap to the decreasing equation, or Q is equal to Q max times 1 minus e to the negative t over tau. And there it is. That's the decreasing. Well, what do we know? And just to be clear, this also works for voltage. Q is just probably what's used for more, but voltage is definitely possible. And what does it say? So, leaking across if it's certain blah blah charge such that the potential difference, voltage, decreases to half its initial value. So it's gone down half. What does that mean? It means that this multiplier is 0.5 once again, or that 0.5 is equal to negative e to the negative t over tau. So from here, we're just going to plug in the numbers. You get is equal to z negative t, so that's going to come from the 5 seconds it told us, because that's how long it took to get to 50% charge, over tau. We don't have tau, but we know that is equal to RC. What's interesting here is it's not giving us that. So it's saying what is the equivalent resistance. So we're essentially trying to find R, or what R would be for this to be true. So tau is equal to R times, but it does give us that capacitance, so 0.2 times 10 to the negative 6 farads. From here, we can switch over and go ln of 0.5 is equal to negative 5 over that RC. I'm not going to rewrite that right now. And then ln of 0.5 is going to be a mess of crap, but essentially negative 0.693 is equal to negative 5 over 2 times negative 6 times R. We're going to multiply that RC over, and we're going to get RC times negative 0.693 is equal to negative 5. Then we're going to divide it. Negative 5 divided by the ln of 0.25. We're going to get R of C is equal to 7.21. And now we know C, so we're going to divide out the C. We're going to get R is equal to an insane number of roughly 3.6 times 10 to the 7th ohms. That's good because dielectric is supposed to be as close to not leaking as possible. So a very high resistance should be expected for this equation. And that's it. So from here we knew that this has to be equal to 0.5, and then we did minus 1. 0.5 is equal to 1 minus e. We did minus 1, you get minus 0.5 plus plus here. Plug in all the numbers, solve. Actually quite easy. You just have to find what to do out of this paragraph that's really not necessary. And yeah. Continuing right along to the next one, we get the values of the components in a simple RC circuit are as follows: C equals 1 times 10 to the negative 6 farads, R equals 2 times 10 to the 4th ohms, and E is equal to 10 volts. At the instant 10 seconds after the switch in the circuit is closed, calculate the charge on the capacitor. So we're assuming there's a switch here, which means that a switch is going to close and it's going to feed into the capacitor, and the capacitor is going to start building up. So we know instantly that this is going to be the increasing equation, or the Q is equal to Q max times e to the negative t over tau. Perfect. Now, and the charge on the, so the first thing it wants is the charge on the capacitor. Well, at t equals 10 seconds, and that's what we're going to solve for immediately. So we know, well, what's the Q max? It's going to be at Q equals CV. So, or 1 times 10 to the negative 6 times that 10 volts, or 1 times 10 to the negative 5th. So 1 times 10 to the negative 5th times e to the negative 10 over tau, and tau is equal to RC again. So so this is going to be 2 times 10 to the 4th times 1 times 10 to the negative 6th. And you're going to get, just plug in your calculator, e to the negative 10 divided by 2x 4, 2 exponent 4 times 1 exponent negative 6 times 1 exponent negative 5. And you can get a very little tiny number. You get 6.738 times 10 to the negative 8th coulombs, and that's the charge. So now we're going to go on to part B. So it's just asking for the current resistor. We're essentially doing the exact same thing, but with current. But the first thing we need to know is what Imax is instead of Qmax. That's the first part. And the maximum current for this one would be when when the capacitor isn't halting the entire thing. When capacitor is letting everything through is when current is going to be at its max. So we have so we can just focus on the 10 volts, and we can treat as if the capacitor is just a wire. So we can look at 10 voltage, and we can look at the resistance, and we can just use Ohm's law to go 10 divided by R, or 10 divided by 2 times 10 to the 4th ohms. It's going to be equal to, I should be able to do that in my head, but I'm not going to. It's like 5 times 10 to the 4th amps. And that's going to be Imax. So, and then from here it's just the exact same equation. So it's going to be that 5 times 10 to the negative 4th times e to the power of negative t, which is going to be 10 seconds. And tau is going to be that same. I actually would like to just write tau down for us, to be honest. So tau is 2 exponent 4 times 1 exponent negative 6, so 0.02. So we go over here and go 0.02, and this is going to be our I equation here, or our I answer of the current in the resistor at 10 seconds. So just plug into your calculator. You get this is going to give us a number, but the number is so small that it's essentially 0. It means that the circuit's been on too long for the capacitor. The capacitor's gotten too strong in 10 seconds that now it's pretty much shut down the circuit. So the number's just too small. If you have a calculator that can give us a number, that'd be crazy. But it's going to be like 0.0 something times 10 to the negative whatever. It's very, very tiny. Negligible. So that's B, is I equals 0. Then we can look at the rate at which energy is being stored in the capacitor. So 1/2 CV squared is equal to the energy. But even though this is true, it's like, actually I'm not going to use yellow. Yellow's terrible. I'm done with it, right? Even though this is true, since the capacitor's already been working for so long, it's essentially shut it down. So the energy, like, there's still a current, but it's really small, and then the energy is still stacking, but it's also going to be negligible to the point where it's essentially 0. And then finally, we have the rate at which energy is being delivered by the battery. So this is the second half.
That's what you introduced to say, right?
All right. So this half is going to be 0 energy, and we're going to have the plus the power, which is I squared. IR squared, sorry, not I squared, IR squared. And from there, it's like, and so, I mean, R has a value, but I, as we found out here, is 0. And energy here, because the capacitor shut it down for so long, is going to be 0. So D is also going to be 0. So literally, B is equal to 0. C is equal to 0, and D is equal to 0. Really, the only real question was this one. But once you understand that, these just all collapse on each other.